Okay, so we're gonna look at just another HackerRank problem here, and this is gonna be the BotClean Large. It should be the hardest out of all the BotCleans, so we'll see how difficult it is. So it's saying that it's labeled as hard. We'll see about that. So the goal here, and there's kind of a lot of exposition, but I think it's best explained through these grids. So we're given our starting position, which here our bot is at 0, 0. He's going to be labeled by B. Then we have these dirty cells, which are all labeled as D in our grid. And our goal is to move on top of them and then clean them. And we want to clean the entire grid in as few moves as possible. So the other thing that we're given is our height and our length. So again, we have a set of moves, and we go left, right, up, down, or clean. Clean just stays in position and cleans the cell. And we just want to traverse our bot B to clean all of these dirty cells. So just like always, we'll try the absolute dumbest thing we could possibly think of first, and then, if needed, we'll optimize. So first things first is to just do a greedy approach. And the way that we're going to do this is first check if we're over a dirty cell. So if board, and I should say we're given our X position, our Y position, our height, our length, and the board. So if board, pause X, pause Y, if this is dirty, then we just print clean, because we're already over a clean dirty cell. Why not just clean it? And then this function should return nothing, so we just go ahead and return none. So now the other thing that we want to do is find the closest dirty cell. So since we're just going to greedily do it, so that's going to involve finding all of the dirty cells, and those are just going to be tuples ij for I in range height and for j in range length. And the condition is that board ij needs to be dirty. Now what we want to do is find the best cell that we're going to go to. So we're going to start that off as none. And the best distance is going to be the smallest distance. So we'll start that out as float infinity so that we can do a compare and swap. So here we just do our compare and swap. So for x, y in dirty cells, we are just going to check if the Manhattan distance is less than our best distance. So what we want to check is if the number of steps we need to take to get from position X to actual X of our current cell plus the distance to get from position Y to the Y value of our cell is less than best distance, then we're just going to say that best distance is equal to that distance, because we're just doing a compare and swap, and then we just swap the cells. So best cell equals xy. Now that we have the best cell, now we have to find the actual move that we need to make. So in that, we just check over the 4 possible moves and see which is the correct one. So if position x minus best cell 1, that should be 0, is less than 0, then that means that best cell 0 is bigger than position x, meaning that the best cell is further down on the board. So we want to print down. And then else, if we have the opposite of that, best cell 0 is greater than 0, then we know that it's further up on the board, so we want to just print up. Now we do the same thing with the y coordinate. So if best cell 1 is less than 0, then clearly best cell 1 is larger, meaning that it's further to the right on our grid. So we want to print right. And then the only move that we have left, because we already did clean, is to go left. So otherwise, we're just going to print, oops, if I could type, we'll just print left, and then same thing. This returns nothing, so it doesn't really impact performance, but kind of helps readability a little bit. So first things first, let's just run the code, see if it actually works. Um. Oh, and I did not end. There we go. All right. Yeah, it really wouldn't be a hacker rank session if there was not a typo. So, okay, so you can see our bot here. He's just going through and cleaning everything, and I guess that's what, 16 moves, which has to be optimal. Yeah, okay, so we finished it in 16. If we go back, it's pretty easy to see that this is optimal. Because we have to clean this one, and then immediately down we have to clean that one. There's only 2 paths to get to this guy, and then we have to clean this, and then once we get down here, it doesn't matter which one we clean. So that has to be optimal. So let's just go ahead and submit the code. Sometimes for these AI ones, especially if it's kind of a large problem, they take a little while to play. But I don't see, there isn't like a loading bar or any kind of status update, so sometimes you have to refresh. This website is like pretty good for certain things, but it's quite bad. Okay, so we won all 4 of our games. So, alright, I guess it's not going to give us a score, so let's just go ahead and check it out. And I think it was 54 is passing. Okay, so we're 0.1 over passing, and it looks like we are 2.3 points within optimal. So, I mean, I'm happy with that, because that means what? That over the entire, all things tested, we were, I think, within some small percentage of optimal for each of them. Let's check what the very last score is. Oh, of course it would be 0. Let's see if there's anything. Okay, well, yeah, so there are a lot of zeros. Yeah, that's not really going to change anything. Alright, so, I mean, that should pretty much solve it. We got 54 for a greedy solution. Oh, and it reset our code. Alright, well, I guess I'll just end it there. If anybody has any questions, feel free to ask. I'll probably post a couple more of these. This one wasn't too particularly interesting, but I do think it's good to kind of see that sometimes things might look like really difficult, but a greedy solution will just solve it. Like, I bet that a lot of people, when they first look at this, they think like, okay, this is a traveling salesman problem. Like, I have to do some NP hard or NP complete algorithm to solve this, but like sometimes, greedy's good enough. So same thing. If you guys have any comments, questions, please leave them, and I'll try to respond to all of them.